Hello everyone and welcome back. In this video we are going to finish this tutorial that we are doing, in which we are creating this mechanism to represent an excavator arm, and we are using only rigid bodies and connectors, and this is going to be solved in Abaqus, and we are creating this model using ANSA, which is a preprocessor from Abaqus. So far we created what you see here. Let me deactivate the visualization of CAD. So now we have just the visualization of the FE module, and this is what we created so far. You should select here the Abaqus deck so that you see the Abaqus database on the left side of the screen. That shows what we created so far. Okay, so if we maximize the element group, you see that double click on rigid body and you see that we have 5 rigid bodies so far: arm 1, arm 2, connecting mechanism 1, connecting mechanism 2, and peak 2. We connected these rigid bodies using connectors. Double click on connectors. We have here 5 hinge connectors. Okay, and we also created one step 1, in which we can open up step manager. Double click on step manager, and also here double click on it, and let's maximize this window. You see that we have one step here. Let's maximize it and see what's inside it. We have 2 connector motions inside this step, and we have one boundary condition. Double click on boundary and you see that this boundary condition is just to fix all degrees of freedom of this node, which is the reference node of this rigid body, which is arm 1. So if we fix all degrees of freedom of the reference node, that means that we are fixing the whole rigid body, arm 1. And then we applied also 2 connector motions. One that is rotation of 30 degrees for this connector, for this hinge connector that we have here, and one rotation of 30 degrees of this connector. Okay, all right, and we tried to run this module as is now, and this is the files that we had as a result. And if we open the .sta file, we have the information about each equilibrium interaction and increments and everything else. You see that we had 5 cutbacks in a row, and that means that we have an issue. We could look at the .msg file to see what is the largest residual force for the last attempt, and the largest residual moment and everything else. But the thing here is that the MSG file is kind of confusing for this situation. So in this case, we should think about the module that we built itself. Okay, we should think about the boundary conditions. We should think about the types of connectors used, and things like that. Let me explain one thing here. We have only rigid bodies in this model, so there's nothing here that can actually deform, and these rigid bodies are connected by hinge connectors. Hinge connectors only allow rotation about its local x-axis. This means that, well, each connector has its own local x-axis, right? And we had defined this x-axis by creating one point on one side, the other point on the other side, and then one point in the middle, and then we created the coordinate system using these points. We did it for every hinge connector that we created. Probably these axis of each coordinate system, the x-axis of each coordinate system, is not completely parallel to each other. which means that there is going to be some disalignment, and therefore, when we apply these rotations, there is going to be an attempt to deform the rigid bodies. So this is the issue, because the rigid bodies cannot deform, and therefore there is this attempt of deformation, but it's not possible, and for that reason the software is not able to converge. So what we can do here is to create something that is going to behave similarly as in a similar manner as a hinge connector, but that is not going to be completely rigid for the other degrees of freedom. We can apply a very large stiffness for the other degrees of freedom, but it's not going to be completely rigid. You're going to understand better when we get to do this. Well, one way to do this is to use Cartesian cardon connectors instead. Let's open up a web page and let's look here for Abaqus User's Guide, okay? And then click on one link that you can have access. For example, this one for this university, everyone can access it. Okay, I prefer to access the User's Guide here because sometimes, I don't know, you don't have the Abaqus User's Guide installed in your machine, or you don't have the documentation installed in your machine. But in here, I'm sure that you can access this User's Guide. Let's go to Elements, Connector Element, Amplify Connector Elements here, and then go to Connector Type, Library. Now let's look for Cartesian. Control F and search for Cartesian. And then here we have the description of what is the Cartesian. Provide a connection between two nodes that allows independent behavior in three local Cartesian directions that follows the system at node A. Let's search for Cartesian again and let's press enter several times until, let me see, until we find this section that talks about the Cartesian. So you see that the Cartesian, we can see that the available components are translations in the X, Y, and Z directions. Okay? Well, using the Cartesian connector, we can connect 2 points and establish a relationship for forces and displacements in the X, Y, and Z directions. Okay, that's what we can do. But you see that we cannot establish a relationship between rotations about X, Y, and Z. So that's why we should also use the cardon connector. Let's Control F and search for cardon. Cardon provide a rotational connection between two nodes parameterized by cardon. Let's press enter until we find this section. And here we have a description of this section. And well, basically using the cardon connector, we can establish relationship between rotations. Okay, so let me show here in ANSA how we can do this, how we are going to establish these relationships. And if you are confused right now, I'm sure that you're going to understand it completely when we get it running. Let me deactivate the visualization of rigid body. And let's double click here in connector, and let's start with this one. And for this one, double click on it. You see that we have one PID for this connector that we defined previously, right? We are going to modify this PID. So press F2 while we have this selected. And here, instead of using a hinge, we are going to select here Cartesian. Search for Cartesian, which is this one. And in this case, we are going to have a component 2, because I want two behaviors, compatible behaviors for this connector. And in here, we are going to have the cardon connector. Okay, we can have this because these are compatible. The component 1 is compatible with component 2, because component 1 is related to translations, component 2 is related to rotations. Okay, in this case. The coordinate system is going to be the same. The x-axis is going to be the one that we are going to have the rotations. In this case, I should define an MID, a material for this connector. MID is just a material, okay? Now you're going to understand what is a material for a connector. I know this is a little weird at first, because we usually think of materials when it's related to solids, when it's related to shell elements or beam elements and things like that. Well, a material here in ANSA is anything that defines, for example, the stiffness of any type of entity. So to create a new material, we are going to use the question mark to open up a list of materials available for a connector. There is no material available. We didn't create anything yet. Right click, new. And then in here, I'm going to give it a name such as, for example, Cartesian, Cardan, Met. And in here we can define many things, many types of behaviors for this connector. Okay. In this case, I want to define an elasticity. I want to define a stiffness for translations and rotations for this connector. So I'm going to say yes here to define it. And then here we should input a data. We should use, well, select this and use the question mark again to open up a list of options. We don't have anything yet, so we should create. Right click, new. And then you see that in ANSA, we usually work with many windows. You see that right now I maybe have 5 windows opened. So you should be very careful, and let me say that you're going to get used to it, okay? In here we can give it a name such as Cartesian, Cardan, elasticity. And then here, these option components, if I say yes, I can define the stiffness of each component. Component 1 is for translation in the local x direction. Component 2 is for translation in the y direction. 3, translation in the z direction. And then 4 is rotation about the x-axis. 5, rotation about the y-axis. And 6, rotation about the z-axis. Now, this part is very important. The hinge connector had the stiffness for translation about the x-axis as an infinite value, which means that it was rigid. In this case, we should define here as yes, we're going to define a stiffness. And then you see that we can define here a value for this stiffness. Okay? We can also define non-linear stiffness, like a curve of force versus displacement that is not linear. We are not going to practice this in this tutorial yet, okay? This type of behavior is important when we are going to model real connections between, for example, front suspension components, because the behavior is not linear, but we're going to talk about it in future tutorials. In this case, we are going to define a linear behavior. And here we should input a stiffness. I usually like to use a stiffness of, for example, 10,000. And let me explain you one thing that is very important at this point. Let's open a web page and let's look for Abaqus units. Go to images and you see that we have these tables here of set of units that we can use for Abaqus. Let's open this one, for example. Maybe my camera is in front of it. Let me deactivate it. And then you see that we can select a set of units that we want to work. In this case, I'm working in the SI millimeters. So length is in millimeters. In my module, force is in newtons. Mass is in tons. stresses in megapascal, and etc. Well, this is the definition of a stiffness. Stiffness is just force per unit length. In this case, for the set of units that we are using, force is in newtons and length is in millimeters. 10,000 means that I need to apply a force of 10,000 newtons to have a displacement between the two nodes of this connector in the local x direction of 1 millimeter. Okay, so I should, for example, if I want to separate, well, at first these two nodes are, let me activate the camera again. So in the current configuration, the two nodes are in the same position, right? If I want, let's suppose that the x direction is in this direction, the horizontal direction. If I want to separate these two nodes in this direction by 1 millimeter, let's suppose that this is 1 millimeter, I should apply a force of 10,000 newtons in my force here to do this. Okay, this is the meaning of this stiffness. This is for the x direction. We should also apply define a stiffness for relative displacement between the nodes in the y direction. Okay, because if we don't do this, then the nodes are not going to be connected in the y direction. So it's not going to be stable. The nodes are going to separate in the y direction with no resistance. So we should define a stiffness here, for example, as 10,000 as well. Okay, 10,000 is usually a reasonable value for when you want to just make something that is approximated. Also for translations in the z direction, let's define 10,000. And well, depending on how this model is aligned, maybe this stiffness is too low and we are going to have too large displacements. And then we must increase this stiffness. But let's see what's going to happen. Now let's define the stiffness for rotation. Well, if I want this to behave just like a hinge connector, if I don't define a stiffness for rotation about x, this means that this connector is going to allow rotation about x without any resistance. There is no stiffness, which is what the hinge connector does. Now, usually I define a stiffness, very small stiffness, because in reality, there is always a small stiffness, a small resistance for rotation. Even for example, let's suppose that we had rolling bearings here. Rolling bearings allow rotation, right? But there is a small stiffness resistance for rotation, even for rolling bearings in reality. Or when we have connections of the type ball joint, that we have many ball joints in connecting suspension components of vehicles. The ball joint allows rotation, but it has a little stiffness. It has some stiffness. So in reality, there is nothing that allows rotation about any axis without any resistance. It doesn't exist. But in this case, we can say that well, there is no resistance. We are going to allow rotation about x. That's okay. Or we can define here yes, and we can define a very small stiffness such as 1,000. Okay, 1,000 is a very small stiffness. In this case, I'm not going to define this stiffness. Okay, I'm going to let rotation about x free. And then we should also define a resistance for rotation about the local y and z axis. In the hinge connector, this stiffness is automatically equal to an infinite value. This is the problem, because that's why we had this model not converging. If this stiffness is infinite, if we want to try to create a small rotation about this axis, it's not going to be possible. So it means that then we would have to have deformation in some region of the model, but everything is rigid. So, well, I usually say that this is an over-constrained issue. And that's why this connector is going to help us, because now we can define a stiffness for rotation about y that is pretty large, but it is not an infinite value, but it is so we can have this rotation occurring. We can define here, well, the unit for this is rotation is in radians, and it is rotation, actually force per rotation, Newton per radians. How much, sorry, not Newton per radians, it is unit of bending moment, which is Newton times millimeter, divided by rotation, which is in radians. Okay, this is the units here. So how much bending moment we should apply in Newton per millimeter, actually in Newton times millimeter, to yield to a rotation of 1 radian. Let me tell you that 1,000 in 1, 2, 3. 1 million Newton millimeter per radian is a considerable high stiffness. Okay, this is usually the value that I use for a high stiffness, and a reasonable value for stiffness. Okay, so this is the value that we are going to assume for this example. Let's also define for rotation about the z-axis. And, well, that's all we need. Okay, so we have now finite values for stiffness, which means that now these connectors can deform in all directions, but there's going to be some resistance for this deformation. Just for rotation about x, that there's not going to be any resistance. It's going to be allowed to rotate without any stiffness. Now let's press OK. And then you see that we have this elasticity created. We can select it to be attributed to our material for this connector. So here we have the ID of that elasticity that we created. If we press F2, we are going to open the card that we defined these stiffnesses. Again, press OK. Now, this is the only thing that we should define for the material of the connector. I know that if it's the first time that you're using ANSA, maybe you're getting a little confused about all these windows that we have here, but you're going to get used to it. Press OK. Now you see that this is the material that we created with ID 2. We can select it. And now we have the material selected here for this connector. So now this is a Cartesian cardan with a stiffness, and this is the orientation of this connector. Press OK and press OK. Let's see now the representation of this connector. Double click on connector, select this one, show only, and this is the representation of a Cartesian cardan connector. Okay, it's a little different if compared with the hinge connector. Let's show all. Now to perform this modification for the other hinge connectors, it's pretty simple because we already have the material that we can use for the other connectors. So for example, let's go to this one, double click on this one. Actually, double click on connectors, zoom in here. Let's get this one, double click, go to PID F2, change to Cartesian, cardan. We don't need to change the coordinate system. We just need to define the material that we had created before. We are going to use the same material here. Question mark to see the list of materials that we have, and double click on this one to select it. You see that the ID of that material is here now. We can press OK, OK, and it's ready to go. We don't need to do anything else. Let's do the same thing for this one. This one, double click, F2 in the PID, change it to Cartesian. Where is Cartesian? Here. And in here, let's choose cardan. question mark, select the material, press OK, and that's ready. Let's change this one. Double click, F2 in the PID, Cartesian, Cardan, question mark on the MID, select this MID, press OK. Let's go to this one, last one. F2 in PID, Cartesian, Cardan, question mark, select the PID, press OK, OK. And let me check if we are finished. Yes, we are finished. Now we can try to run it. But before, there is one very important thing to do. That is, well, for the test 2, I'm going to just delete everything. Well, let's do a test 3 folder. I'm going to create a new folder, test 3. And the important thing to do here is to go to materials by clicking here, materials. You see that this is the material that we created. It's a connector behavior. It's to define the behavior of a connector, right? And in ANSA, this is classified as a material, a type of material. You see that it's not defined, which means that if we output the .inp file for Abaqus here from ANSA, this material is not going to be defined in the input file. Well, this is something that I don't like, because every time that we create a new material, it's not defined automatically. So we should always define it manually here. We should click here to define this material. If this column is not showing up for you, click here and search for defined and select it here, so that we are going to have this column. And you should have this material defined. Close. Now, before we output these, let's go to compress, all decks, deselect, select, details. Let's roll down to see if there is anything that is going to be compressed. Well, there is nothing, so we don't need to compress these. Now we can go to this folder that we created, copy the path, and then file, output, Abaqus. Paste, let's delete here and paste the path to that folder here, press enter. And then this is going to be test_3.inp. Don't forget the .inp, it's important. Save, and then in here, the version of Abaqus that you're going to run, all, and in comments, none. I don't want any comments, press OK. Now we have the .inp file here, double click on this text file, we have the definition of nodes and everything. So what I was talking about is here, connector, search for asterisk connector. Let me see here, what is the, connector behavior. Yeah, search for connector behavior, and you see that we have here the definition of the connector behavior for this connector. We have the stiffness for X, stiffness for Y, stiffness for Z, and stiffness for rotation about Y and Z. If we didn't define this material in ANSA before outputting it, then this would not be written here, and then we would get an error when we try to run this. Okay. Now to run this, I'm going to open in terminal this folder, so that the, well, you can also search for command prompt, but then you should go to this folder by typing cd space and the path to this folder. When I right click on a folder and click on open in terminal, you see that the command prompt opens already in this folder. So that's why I do this. And then to run this module, I'm going to type Abaqus job equals the name of the job, that is the name of the input file but without the .inp, and then space, and we can specify the number of CPUs that we want to use. That is the number of threads that we want to use. In my case, I'm just going to use 2 CPUs because it's a pretty fast module to run. And press enter. And let's see if this is going to work. Hopefully it is going to work. Now in the folder that we have this module running, we have the files that are generated. And the .sta file has the information about the increments. Well, this is finished. Now let's open up the .sta file. And you see that now it has worked. So it started with 10% of load application, and then it applied more 10%, and in total 20%. And then it found it easy to converge, so it's increased to 15% the next increment, and in total 35%, and then increased to 22.5%, and until we have 100% of those rotations that we applied. Now to post-process the results, that is to read the .odb file, that is the file that has the results of this analysis, we can use a post-processing software, and there is Meta from Betakai, which is the one that I use and I recommend you to use. You can use Hyper-V as well. You can use even Abaqus Viewer. So if you have Abaqus installed in your computer, you can go to Abaqus Viewer. This is the application that can be used to read .odb files. Okay, you can use it, but in my case, I'm going to use MetaPost. I'm going to search for Meta, which is also from Betakai, and I'm going to use the default layout. Press OK. And again, let me tell you that this video is not intended to show you how to install these softwares, okay? You're supposed to have it, or you should try to find a way to download it. Or you should use the one that you have in the company that you work, if you already work in this area, in a company that has this software, which is the most recommended thing that I think. Let me point out again that if you want to read Abaqus results here in Meta, you should install the Abaqus library. Okay, if you don't do this, you're going to have an issue. So this is another thing that you should find and install it. Okay, let me tell you that it's not hard to find it. Okay, now this is the working folder. We have the results here. I'm going to copy the path to this folder, Ctrl+C. And in Meta, the first thing we should do is, you see that we have geometry selected here, this tab, right? And then here we should input the .inp file that has the information of nodes, elements and materials, properties. I'm going to Ctrl+V the path to that folder here. And in here, I'm going to open up the .inp file. Double click. To rotate the view, you should hold the Ctrl key and use the left mouse button, just like in ANSA. Here we have the module that we had defined, but we don't have the results yet. Now to see the results, we should go to Results tab, and you see that it has selected the .odb file automatically, but if in your case it didn't, you should click on this folder and you should select the .odb file here. Here we have those increments that were used in this analysis. And if we go to Scalar tab, we can choose the type of result that we want. In this case, I'm just going to calculate displacement magnitude as is selected here. Now I'm going to click in Read, and then we have the results read. Now to animate this to see how this is moving, we can use this button here. So if we click here and drag it to the left, we are going to see this mechanism working. Well, apparently this is working as expected. We have a rotation of 30 degrees here. And we also have a rotation of 30 degrees here. Look what happened when we have this rotation of 30 degrees here. This is important that you understand. When we have this rotation, then we are going to have this, well, let me get here, yeah, let me do this manually. Yeah, I guess, let me take a screenshot of this. We can do this sketch in, well, I guess we can do this here. So we are having a rotation here, right? Well, red is not the best color here for this scenario. Let me get maybe blue. Rotation of 30 degrees about this connector, right? When we have this rotation, we have a force that is happening here between the purple rigid body and the green rigid body. And then when this occurs, we also have a force that is occurring here. And this is why this rigid body is rotating like this. Okay, let's go back to this animation. And you see the peak tool is rotating as well. So this is how this mechanism works. But this mechanism doesn't work with rotations that are applied directly here. It works with the hydraulic actuators that actually creates a force. Let me just Control Z everything here. There is going to be the hydraulic actuator connected here. And this hydraulic actuator is going to create a force like this here. And this is going to make this rotate. We are also going to have a hydraulic actuator here and also here. Okay, this is going to pull it like this, and it's going to make the red rigid body rotate like this. Okay, this is how it works. And well, now let's continue here building this module. Now let's activate the visualization of the CAD by clicking here. And let me think what we can do now. Well, I guess that the next step is to create this rigid body. Let's think what can be included in this rigid body. Well, you see that I'm going to select everything that I guess it should be included in this rigid body. Let's use this tool to isolate, and let's select here, click here and hold, and then select PID. And in here you should have the visualization, the draw mode as PID as well. Okay. Now, I guess that this, let me think here. I guess that this gear is part of the rigid body that we are going to create. Also, this one, this plate, this one. And, well, even these rolling bearings. Okay, well, even these bolts maybe, but I guess I'm not going to include it. Let's remember that we are creating these rigid bodies just for visualization purposes, okay? So we don't need to have everything. We just need to have some parts so people will understand how this, what is what, okay? These other parts here, I'm going to consider that this is a base that is fixed. So it's not going to translate, it's not going to rotate eventually. Now that we have everything selected, let me also select these bolts. Bolt and washer. Middle mouse button. And then here I have everything that I wanted for this next rigid body. Okay, well, I understand that. Let's lock this view by clicking here. And I understand that this whole thing is going to rotate about, well, you see here the coordinate system that we have. It's going to rotate about the y-axis, the global y-axis. Okay, it's going to rotate like this because of this gear, right? And these rolling bearings is just going to be used to slide on top of that other part that we have below it. To see it, click here in invert. So these rolling bearings is going to be used to slide here on this plate. That is going to be fixed. And there is also this, you know, this path for the rolling bearings. Well, this is how I understand how this works. And well, what's this? Maybe this is just the representation of some engine in a simplified manner. I don't know. Let's click in show all again. And since we have this lock to the view, then the show all is going to be this view here that we had locked. Now the procedure to create this rigid body is the same. We are going to go to classic mesh, length, select everything, middle mouse button, 20 millimeters. Maybe the gears are not going to be so well represented. Let's see. And then let's use the free algorithm. Select everything, middle mouse button. Oh wow, I guess this is good enough. Okay. This is good enough for me. I just want to people to understand what this part is. And then go to volume mesh, release, select everything, middle mouse button. Now the mesh is not attached to the geometry, so we can deactivate the visualization of macros, and we are going to see the elements isolated. And then go to Abaqus deck, inside elements group, utilities, change type to the entities. I want to transform to R3D from shell. Select everything, middle mouse button, close these, go to elements rigid body. We have this new rigid body, double click on it. Let me say that this is the rotating basis. Copy this name, go to the element set related to this rigid body, F2, and paste this name here and add rigid elements. Press OK, press OK. Okay. Now let's deactivate the lock, show all. And yeah, this is the other rigid body that I want. Now I need to create a connector here to connect these two rigid bodies by using the same technique that we had used before, but in this case we should use the Cartesian connector. Let's go to classic topo. Let me deactivate my camera. On COG circle, select 3 nodes for this circle on the other side as well. Now on COG of points, select this point and this point. Now we have this point right in the middle. Deactivate the visualization of rigids. Let's go to Abaqus deck. Coordinate rectangular from this to this. Middle mouse button. Rotation about y minus 90. I explained why we have this rotation several times before. Click on OK. The x-axis is in the axial direction of a bolt that would pass through here. Now let's create the connector to nodes from here to here. Middle mouse button. Drag the module browser like this. Select the connectors part that we created previously. Let's create a new connector section. This is going to be the rotating basis to ARM1 connector. Cartesian, Cardan, question mark on orientation 1, select this coordinate system that we just created. And then in MID question mark, select the Cartesian cardon material that we created. Press OK. Select this connector session that we just created. We have the ID of this property here. Press OK, and the connector is created. Close this. Now, we should go to rigid body, arm1, double click on it. We have the tie node set. We should include one of these nodes on this tie node set. Get the ID of this tie node set, Control C, ID is 3. Go to sets, search for ID 3, which is this one. Right click, modify content. Let's maximize here. We have only one node in this set. I'm going to select this node to be the other node for this set. Select it, and now you see that we have two nodes. Okay, you should always manage how you are modifying this set. Because if you deselect the other node that we already had in this set, then this mechanism is not going to work, and then you're going to need to find why this is not working, and you're going to spend some time. Middle mouse button. Let's check. We have two nodes now, and one of these nodes is this one that is highlighted. Now we should create one additional node set, new, and select this node, the other node. Middle mouse button. The name is going to be rotating basis tie node. It's a node set, and the ID is 12. Let's memorize this. The ID is 12. Click on OK. Now let's go to rigid body, rotating basis, double click, and define the tie node set as 12, which is the ID of that node set that we created that has this node. Press OK. Now let's match the position of these two nodes using here in the Abaqus deck. Let me just minimize these like this, so we see the Abaqus deck here. Use the match function inside the node group manual. Let me activate the camera. From this to this, middle mouse button. Now we have two nodes in the same position. Well, yeah, we are finished. Now these two parts are connected. Let me show rigid elements. Okay, now these two elements are connected. These two rigid bodies are connected by this Cartesian cardon. Now let me show CAD. And now the other rigid body that is going to be the one that is going to be fixed, in my opinion. Oh, there is even a rolling bearing here. Oh, okay. This is probably for this upper structure to rotate about the global y direction. Well, in this case, let me think here. I'm going to consider everything else that we have here as another rigid body. No, actually, I want to do one thing here that is going to be cool. Maybe we are not going to finish this tutorial in this video. We are going to have one additional video because I want to create a connection between these two gears in a way that they are going to rotate. We are going to use an equation here. Okay, and for that reason, I should have this small gear as a single rigid body. Maybe together with this axis, because these axes rotate together with this gear. Well, the rest can be only one single rigid body. You're going to understand eventually why am I doing this, like this. So let's use this tool here to isolate by PID, create a box selection like this, so that you're going to get all these parts that are in this region. Zoom in and also select this. and create a box selection like this to get all these parts. Okay, now we have everything that I want. Middle mouse button. See one thing here. Yeah, okay. Well, I need to hide. Let's use this tool to hide. By PID, select select just the gear. Okay, because you see that this axis is modeled together with this part, which is, I guess, the representation of a electric engine in a simplified manner. Okay, so we're going to create a rigid body that is going to contain everything that you see here. Okay, you're going to understand eventually why. Now let's go to classic mesh, length, select everything, 20. Free, select everything. We have the mesh created. Yeah, well, this is not good at all in these regions. It's not looking good, but I'm not going to spend time working on it. Let's just accept it as is. It's not going to change the results anyway, and we are going to spend too much time fixing this, which is not the focus of this tutorial. So let's go here to volume mesh, release, select everything, middle mouse button, deactivate the visualization of macros, go to Abaqus deck, utilities, change type to the entities, from shell to R3D, select everything, middle mouse button, close this, and yeah, that's what I wanted. Well, this is very bad, but that's okay. Okay, so let's now show all to see the other parts. Let's double click on rigid body, and let's change this as being the fixed basis. Okay, this is the fixed basis, and copy this name, F2 in the element set, and paste this name here. Okay, and okay. And now let's create the connection that we have between, double click on rigid body, between the fixed basis and the rotating basis. Okay, well, in this case, deactivate the visualization of FE entities by clicking here, and activate the visualization of CAD entities by clicking here. Now we can see only the CAD. Now, well, we can imagine how this works, right? The rotating basis is going to rotate about the axis of this tube that we have here with respect to the fixed basis. Okay. Well, this rolling bearing is not, well, probably there is some other things here below that is not represented in this CAD, but that's okay. But, well, I'm pretty sure that this is how this mechanism works. Okay. And the rotating basis is going to slide on top of the fixed basis by these rolling bearings, okay, that are going to be in contact with this surface. To create this relationship, we can use the hinge connector. In this case, we can use the hinge connector. That's okay. Because the local axis of this hinge connector is going to be completely different, it's not going to yield to any over-constraint issue. But, well, yeah, well, let's create this hinge connector. Activate FE. Oh, actually, let's create 2 points here by using the CAD. Let me deactivate the camera. Go to Classic, Topo, on COG, of edges, zoom in here, and I'm going to use this edge here. See? To select this whole circle, you can use this tool, loop, activate it, and then position the mouse here, and you see that it already selects the whole circle. Select it, middle mouse button, and then one point was created right in the middle of that circle. Let's check it. In the database, scroll down, double click on point, and there we have it. We have the point created there. Now let's do the same thing here again. Close these. Well, you see that in my case, I'm not being able to close this. Sometimes this happens in ANSA. To close this, I should click here in this quit browser list, because there was another thing running and then I couldn't close this window. Now I can close it. Now let's use on COG again, edges. Now I'm going to get this upper edge. Middle mouse button and close this. Why did I create these 2 points? Because I need 2 points to define the direction of the x-axis for the hinge connector. Now let's do one thing here. Let's deactivate the visualization of CAD. Here we have the 2 points we created. Okay, let's go to Abaqus deck, coordinate, rectangular. This is the origin. This is the point that defines the z direction. Middle mouse button. Rotate about 2 minus 90 so that the x-axis is going to be in that direction and not the z-axis. Press OK. Now we have the coordinate system created. We cannot see it because the visualization of FE entities is deactivated. So click here to activate, and let's deactivate the visualization of rigid elements. So we have the coordinate system here. Now let's create the connector. Actually, let's do one thing here. Go to classic topo on COG of points and create 1 point right in the middle of these two. Middle mouse button, and there we have it. Abaqus deck connector, 2 nodes from this to this. Middle mouse button, question mark on PID. Create one new connector section. This connector is going to connect the rotating fixed base. This is going to be, well, in this case we can create, actually we are going to have that connection between the 2 gears, so we are going to have other axes. Well, let's try to use a hinge connector here. If it doesn't work, we can use the Cartesian card. Hinge. The orientation of node 1, question mark, select this coordinate system, double click on it, and press OK. Select this connector section, and here we have the ID of it. Click on OK. Close this. Okay. Now we should include one of these 2 nodes in the tie node set of the rotating bases. Let's do this. Go to sets. We have the tie node set of the rotating bases here. I'm going to modify it, modify content. We have only 1 node for this node set. I'm going to select this upper node here. Now we have 2 nodes in this node set. Middle mouse button, create a new node set, and select this node, middle mouse button, and this is going to be the fixed bases or base tie nodes. It's a node set. Copy the ID of this node set, which is 14. Close these, go to rigid body, and let's go to the fixed basis and paste the ID of that node set that we created. And now we have the tie node set of this rigid body defined. Press on OK. And now we should match the position of these two. Not necessarily, we could let it like this, but I usually like to have the two nodes in the same position. To do this, let's use the match function in the Abaqus deck node group manual from here to here. And now these two rigid bodies are connected. Let's activate the visualization of rigid. Okay. Well, yeah, I'm not going to be able to finish this example yet. In this video, we are going to finish this in the next video because I need to model yet the hydraulic actuators and also the relationship between the two gears that we have here. I didn't create the rigid body for the other gear yet. But before we finish this video, let's make a test and see how this is working, because now it's going to be really nice because we have more parts in it. Let me close this meta. Well, we are going to modify one thing here. Double click on boundary, and you see that we have this boundary condition that fixes all degrees of freedom of this node, which is the reference node of ARM1 rigid body. But now I want to move this rigid body, okay, by applying a rotation in this hinge connector that we have here. What I want to be fixed is the fixed basis. So let's change one thing here. Double click on this boundary condition. You see that in the card that we have the definition of this boundary condition, we have the ID of the node that is being fixed. We should change the ID of this node. Close this. And what should be the ID of this node? Well, it should be the ID of the reference node of the fixed base rigid body. Let's get it. Double click on the rigid body, double click on fixed bases, and you see that this is the ID that we want to fix. Control C this ID, let's copy this ID. And let's go back to boundary, this one, double click, and let's erase this ID and paste the ID that we had copied, which is the ID of the reference node of the fixed bases. Press OK, and now you see that we have this boundary condition applied there, which is the ID of the node of this rigid body. Okay, now this is going to be fixed. Okay, and I want to apply a rotation for this hinge because now I want to see this rigid body also moving. And one thing that is going to be interesting is that I want to also apply a rotation for this hinge. Actually, we have a Cartesian card here and a hinge here, right? Because I want to see this whole structure rotating about the global y-axis. This is going to be really nice. Okay, so let's do this. In the boundary, in the connector motion, we have these two connector motions. I'm going to even increase this to maybe, well, I have here 0.523 radians. I'm going to increase it to 0.8. I don't know how many degrees it's going to result. It's going to be more than 30 degrees, which is nice because we're going to see this moving more. Let's say okay, and let's change this one too to minus 0.8. Okay, it's going to be nice. We are going to see this moving more. Now let's create another connector motion, and to do this, go to Abaqus deck, boundary condition, connector motion element. Select this Cartesian card, middle mouse button, displacement about the local x-axis, which is rotation about x. Oh, sorry. 4 is rotation about X. And I'm going to apply here a rotation. Let me think here. Well, the X is in that direction. Using the right-hand rule, a positive rotation is going to be a rotation in the clockwise direction here, which is what I want. So I'm going to apply maybe a rotation of 0.5. This one, I guess it's not a good idea to be so large, because it's going to move too much. Could be just approximately 30 degrees, which is 0.5 radians in step 1. Press OK, and let's create another connector motion. Now for this hinge here that we have created, this hinge. Middle mouse button, rotation about X, and this one can be large, can be 1, for example. And in the first step, press OK. And I guess this is ready to go. Let's see what's going to happen. Let me go to materials. Let's see if everything is defined. Let's use decompress. Alt X, details. There's not, well, there are 60 nodes to be compressed. Press OK. Now let's create a new folder, which is test 4. Copy the path to this folder, file, output, Abaqus, paste the path to that folder here. The name of this one is going to be test 4. Save 22, all, non-comments, press OK. We have the input file here. Right click, open in terminal, Abaqus space job equals test underline 4, CPUs equals 4. We don't need to specify how many CPUs. We can just have this as we see here. Press enter. The job name should be the same name as the .inp file. And we should be in the folder that has the .inp file, okay? It should be our, actually you should be careful with that. This is running. I'm going to open a, well, let me show you one thing here. Let's wait to finish. Let me double click the .sta file just to see what's happening. Okay, it's running. 84%. Let's wait. Let me close this. Okay, now this is finished. Well, one thing that we can do here is to use the Abaqus viewer application. Click. Now that we have Abaqus viewer opened, we can click here in open database to open a .odb file. Or if you close this window, you can just click on file, open. And then we should go to the folder that has the file. Let me search it here. Oh no. OneDrive, documents, learn FEA. Okay, .odb, and here we have it. I don't really like to use the software, but if you are used to it, you can use it. And in here we can go to result, step frame, and then you can activate the deformed shape like this. Go to the first increment. This is the original state. And then with 10%, this is what happens. 20%, and so on. We can animate it by clicking here. Oh, this is nice. But well, you can use it. I don't like it. I'm going to close it, and I'm going to open up MetaPost. In MetaPost, default layout, it's okay. And here, let's go to the file to the folder that we have the results. Control-C. In geometry, we should input. Let me Control-V that path here. We should input the .inp file. This is very beautiful. You see that's why I like MetaPost, because it's much more practical than Abaqus Viewer. Go to results, and we have the increments used to solve this analysis. This is a nonlinear analysis because of large displacements. And let's go to scalar. I'm going to plot displacement magnitude. Read. Okay. Oh, I forgot to activate the camera. Well, now we can use this button to see how this is moving. And this is perfect. This is moving. Well, this is not perfect because the rotation that is occurring here is in the opposite direction that I wanted. So you see that there is this overlap. To fix this, it's pretty simple. Let me teach you one thing that is very interesting here. This is going to be interesting. In MetaPost, click on File, New, and then clear existing session, reset everything. Okay. In this folder, we have the .inp file. Open it in a text editor, search for step, asterisk step, and then in here, we have the definition of this rotation. Actually, it is this rotation that is not in the right direction, which is the rotation that we applied for this connector here. This rotation here should be negative. Just add a negative sign. Okay, add a negative sign here. And save this file. And then go to the CMD that we had used to run this one, and let's put it to run again. Actually, it's not this one, I guess. Let me just close this just to be sure that I'm not. Yeah, this is the one that I had used previously. This one is already in the folder that we have the .inp file. I'm just going to use the up keyword, and then I'm going to run this job again. Now the input file is modified. It's asking if I want to overwrite, because I have already ran it. So press Y and press enter, and this is going to be overwritten. This is running again. So you see that when you want to make small modifications in your module, you don't need to open up ANSA, do this modification there, and output the input file again. You can do this directly in the input file. It's important to do this. It's important to know how to do this. It's a good practice. Okay, so this is finished. We can go to MetaPost again, geometry, input the .inp file, results, and here you should input the .odb file. In my case, it's already inputted automatically. Read, and let's rotate it, and let's see. Yeah, this is perfect. This is really nice. This is what I wanted to happen. Okay, this is how this mechanism works. Well, we can click on this button to create an animation. This is too fast. We can configure this animation, but I'm not going to do this here because there are some things that we need to do yet. And then eventually when we get to post-process the final module, we can configure some things here. Okay, and I'm going to also talk how this module can actually be used for a structural analysis, because right now we are just doing something that looks beautiful, but how can we actually use it to verify the durability of a component here, how we can use it to perform a structural analysis itself. Okay, I'm going to discuss about it in the next video after we finish modeling this module.